this is too dark. Sorry, guys. All right, guys, let's get started. And today we're going to talk about timing analysis. We've been dealing with the functionality of a combinational circuit. So today we'll delve into the more fine-grained details about the execution behavior of a combinational circuit by looking at how signal changes over time. I didn't touch anything. Let me set the brightness right. Yeah, the control panel doesn't seem to work very well today. I'll probably go to the back in a few moments to turn it back on. So, and then we're going to see some new components for building combinational circuits. We have seen how to use different gates, AND, OR, NAND, NOR, XOR to build different functionalities. And today we're going to see more components. So here's where we are. We talked a lot of things about combinational minimization, different analysis methods, different representational schemes, and different implementation tools. We start with Boolean expression and truth table to represent functions. And then we can minimize function by either applying Boolean algebra or through cardinal map. And through K-map, we typically find prime implicants and essential prime implicants. Or you can also use the quiet McCluskey method using tabulation, prime implicant chart, together with Patrick's method to minimize larger functions in a more automatic way, in a fashion that is computer friendly. And finally, the goal is typically to find the minimal SOP or POI circuit. And you can also show that in a circuit diagram. And if you want to do multi-level conversion, you'll do the regular two-level minimization first, and then apply a little bit of distributivity to get multi-level, and do some local transformation to get NAND or NOR-only implementations. Right? So I would like you to spend half a minute thinking about what is one thing that you learned really well, or one thing that you didn't learn really well, and what is the reason for that. Half-minute timer starts. What is one topic that you think you learned really well? I'm going to deal with the light situation. All right. All right. Does anyone want to share with us what is one topic they learned really well, or they just really like, or really hate? Anyone? Yes.
Well, I don't see Boolean algebra, but the other one is Patrick's method. Not good at that because I didn't go to class because I went to the beach.
I see. Patrick's method. Patrick's method is not an easy task. It's because it really represents a larger theory of Boolean satisfiability, and this one instantiation does require some foundational understanding of the way we model a problem into expression and then create new variables, doing that transformation, etc. Yeah, that one definitely you can probably benefit from a bit more practice. Anyone else want to share with us? And you also said Boolean expression, just Boolean algebra in general. Yeah, it's a new algebra. You have to get comfortable with all the new transformation tools and all the rules, like different way of applying distributivity. Some of them are a bit unnatural, right? So that is understandable. Anyone else want to share with us? Yes, Eric. Mm-hmm. Let's see, the prime implicant chart and Patrick's table. Yeah. So you see, prime implicant chart is a way to solve a cover problem using a set of rules to cover a set of elements. And again, it's a new representation. I only use it for one purpose, even though in real life, that kind of problem has a lot of different applications, and then you might want to use it to solve many other problems as well. So yeah, every new representation comes with some new challenges. Yeah. Rona? Any ideas?
I was thinking the same as.
Uh-huh. I see in the prime impedance chart. I see. Yeah, I think sometimes it's beneficial to think about the correlation between the prime impedance chart and how you do K-map, because K-map provides a great amount of intuition, right? And essentially every circle that you put in the K-map for those prime impedance will translate into one row in the prime impedance chart. And essentially you're solving the very same coverage problem, right? Just in K-map you have like a two-dimensional coverage relationship. In a prime impedance chart, everything goes in all the impedance goes to one side. So yeah, think about the correlation of these topics a bit more. All right. And with that said, today we're going to move on to timing analysis. Let me also switch my presentation device. All right. So timing analysis is dealing with the delay or latency of a circuit, also individual gates. So gate delay, every gate has a delay. So for each and every gate, let's say we have a bunch of NAND gates over here, NOR gate, AND gate. It takes some time for us to go from inputs to outputs. Like when we put down some values at the inputs, the output doesn't get updated immediately. It takes usually a few picoseconds in current technologies. So for example, take Intel i9-11900KF, which supports turbo boost. But let's forget about all those advanced features. And this processor has a frequency of 3.5 gigahertz, which means if you do the inverse of that, you get the cycle time. So every cycle needs to complete within about 285 picoseconds. And nowadays, circuits typically have somewhere between 10 and 20 levels. So let's say the circuit has 14 levels. That translates into a gate delay of 20 picoseconds. 20 picoseconds. Picoseconds, it's like a very fine unit, right? So it happens really fast. But you have a lot of gates to process. And so overall, 285 picoseconds is your overall latency of your whole combinational circuit. So you can send in a new input every 285 picoseconds and get the result at the end, and then send in a new set of inputs. And this is a hypothetical calculation ignoring all the turbo boost features. The processor can also run at a faster frequency using turbo boost, at about 4.5, 4.6 by increasing the supply voltage. But let's forget about it. So what I have on the right is it's a circuit diagram of an 8-bit ALU. ALU stands for arithmetic logic unit. It's really a component consisting of adder, subtractor, shifter, incrementer, bitwise OR, bitwise AND, a reconfigurable arithmetic logic unit. And this very old 8-bit unit has, so let's say how many levels? We have 1 level, 2 levels, 3 level, 4 level, 5 level, 6 level, 7 level, 8 levels. Right? This 8-bit circuit has 8 levels of combinational logic. So you can imagine that nowadays we're dealing with 64-bit circuits. So they will probably have a few more levels. 14 level is not an unreasonable guess. And there are two parameters that we care about for a combinational circuit. Number one is called the propagation delay, which is the maximum time it takes for input change to propagate to the output. And that is usually what we consider to decide the frequency of a processor. We need to make sure that all the computation can complete within, let's say, that 285 picoseconds. And to find the propagation delay, we look for the longest path in the circuit, the path that goes through the most gates. In this case, it's going to be A through 1 gate, 2 gates, and 3 gates. And let's assume that every gate has, let's say 10, 20 picoseconds of delay. So we just add up 3 gate delays. That gives you your overall propagation delay, the longest delay. There's also a concept called the contamination delay, which is the shortest time for some input change to start changing the output value. Right? May not really complete the computation by that time, but that is the shortest path where the output could change. So for example, if you keep ABC stable and only change the D variable, it will propagate to the output after just 1 gate delay. And that is the shortest path in this circuit. And we care about both of these delays for different reasons. We care about propagation delays because if the circuit runs too slow, the output is not ready when we need it. We want the circuit to work at a good enough frequency to support all the computation, any kind of binary Boolean inputs at the inputs of the combinational circuit. But if the circuit runs too fast, which means the contamination delay is too small. We're also going to run into some issues. So let's say you send me one input, I do some processing. And you send me another input. I might still be processing the previous outputs for that previous inputs that you sent me. So the receiver needs some time to process the previous output. And if you send your next input too early and the contamination delay is too short, I might not have enough time to process the previous output. So if the circuit runs too fast, I may not have enough time for the receiver to process the previous output. So I want to make sure that essentially the circuit works very nicely within this propagation delay so that any computation can complete within my cycle time. And also, I don't want my output to change too fast to save enough time for the receiver to process the previous output. And in this class, we care mostly about propagation delay, the longest path of the circuit. And to activate this path, not only do we need to assign some Boolean values over here, we also need to make sure that these values allow the propagation of that signal. So for example, the other input to the AND gate, I set it to a constant 1 so that whatever I change on the other side can be propagated to the gate output. If I put a 0 over here, it will directly set the output to 0 and block the impact of that input. So when you are selecting this variable that can propagate, that can activate the critical path, the longest path in the circuit, we also need to set all the other input values to their propagating conditions. Right, for these gates, that's essentially the identity element, the element that allows the other signal to flow through the gate. All right. And in reality, these equations are a lot more complex. The propagation delay and contamination delay vary for each gate. Different gates and or NOR, they have different propagation delays. They will also vary for the rising and falling signal changes. So for the output to change from 0 to 1 and 1 to 0, they'll have different delay behaviors. And also, they vary based on the gates that a gate connects to. Essentially, the other gates driven by a given gate. The more gates you drive, the longer of a propagation contamination delay that driving gate will incur. So really, these delays are calculated based on a variety of parameters, and you probably never have to calculate them by hand. If you really pursue a career in electrical design, this calculation will be handled automatically by electronic design automation or EDA tools. So they have a library of all these parameters, all the information, the physical composition of these gates to make a precise estimation of all kinds of delay behaviors. And can even give you, let's say, the top 10 longest paths, the bottom 10 shortest paths for you to more accurately analyze the propagation and contamination delays. All right. So I have another example at the bottom, a different gate with 5 NAND gates. Right, let's say the propagation delay is for each gate is 4 nanoseconds and contamination delay is 1 nanosecond. Again, to find the overall propagation delay, you look for the longest path and add up their propagation delays. In this case, it's going to be the path through the top. Right, this one goes through 3 levels of gates. That's the maximum number of levels. There's an equivalent going through the B side. B is through 3 gates, reaching the output. And let's say every gate has a 4 nanosecond propagation delay. This overall critical path will have a 12 nanosecond propagation delay. Right. And in the meantime, to activate that path, I need to set the other input values on the off side of the path to the propagating condition. So I need to make here logic 1, and the output of this gate a logic 1, so that the output depends strictly on that input. Right, and that can be done by setting B to be a 1. And 1 gives a 0, 0 produces a 1, so everything gets satisfied. Similarly, when looking for the shortest path, well, this is a very short path that goes through only 2 levels of gates. So the shortest time that the output could start to change would be the contamination delay of each individual gate on that shortest path, which is 1 + 1, 2 nanoseconds. And again, if you really want to activate that path, you probably need to have some propagating values on the other side of the path, right? Just to really propagate that shortest signal to the output. Any questions so far? Yes, Mitch.
Can you summarize the past slides so far?
The what?
Can you summarize everything so
Okay, so we're talking about how to count the time it takes for inputs to reach the outputs. And the natural way of doing that counting is to find the longest path. And your circuit frequency has to be decided based on that longest path to make sure that any computation can happen. And that is called a critical path. And the longest delay on that path is called the propagation delay. Right. And we also care about the shortest path, just in case someone is still processing my previous output, and I don't want the output to change too early for the new input. Right. Again, we can define different propagation and contamination delay for each gate, and also for this overall circuit by looking for the propagation delay of the longest path and the contamination delay of the shortest path. So the biggest of the biggest and the shortest of the shortest. Yes?
Are the longest and
Yeah, it is. Yeah, how many gates that path goes through. Yeah, any more questions? Yes, Ben.
can you have like multiple?
You could.
You have that one.
Yeah, you could. Yeah, this would be another shortest path. Yeah, again, like we're not really worrying too much about those parameters. So given that circuit diagram, and let's say delay only depends on the gate type. So you could have multiple longest and shortest paths. All right. So how do we analyze the exact timing behavior of the circuit? When you change the input, when does the output change? And not only just the output, when does each of these intermediate signals, let's say G1, change? We can characterize it by drawing a timing chart or timing diagram. So timing diagram shows signals as a function of time. So over time, how does each gate output and the primary output change? So I have an example over here. Suppose my initial input is 0, 1, 0, and I change my A from 0 to 1 at time 40, whatever time unit I define it to be, and then I change it back to 0, 1, 0 at time 100. So what I can do is I can draw the timing graph or timing diagram for it by just putting down these signals and show these input signals and also intermediate signals as a function of time. So let's say my input. Okay, let me find a good color. My input A starts with 0. So we essentially put down a line 0 until T40. And at T40, A goes from 0 to 1. So we let it go up. And then it will stay at 1 until time 100. That's about time 100. And it's going to go back to 0. So the low level of the signal indicates a 0. The high level of the line indicates a 1. Right. And in this case, B stays at 1. So I'm going to draw B at the high level throughout my evaluation period. C remains a 0. So C will just stay at 0. Right. That's how you represent these three input signals in the timing diagram. And let's do some evaluation. So at the beginning, input is 0, 1, 0. So 0, 1, 0. The output here should be a 0. The final output should be a 1. I'm just evaluating through the gates. So at the beginning, my G1 would be a 0. And my G2 is a 1. And they're going to remain at that value until at least time 40. Right, that is my initial condition of the circuit. So at time 40, I change my input, A from 0 to 1. And the first gate has a 20 nanosecond propagation delay, or in this case, just delay. Like we're not differentiating contamination and propagation anymore, right, for the simpleness of evaluation. So let's say the gate has a 20 nanosecond delay. What that means is that when your input changes time 40, the output will change at time 60. So 20 seconds after your input change, the output of that gate will change. So G will remain at 0 until actually time 60. And that point is going to change up to a 1. Right. And similarly, when your input A jumps from 1 to 0 at time 100, the output will change after another 20 nanoseconds back to 0. We just did a single gate evaluation. Input changes twice. The gate output also changes twice, right? But after a 20 nanosecond delay. So from here to here, that's 20 nanosecond. From here to here, that's 20 nanosecond. That's the latency between G1 and the A input. And similarly for G2, G2 depends on G1 and C. C never changes. So whenever G1 changes, so let's say G1 goes from 0 to 1, the NOR will evaluate to 0, and that will happen after 20 nanoseconds of delay. So I'm going to continue getting this until time 680. So 20 nanoseconds after G1 changes, get it back to 0. And then when G1 changes from 1 to 0 after 20 nanoseconds, G2 will change from 0 to 1. Again, we have a 20 nanosecond delay from here to here and here to here. That is a gate delay. Yeah. Any questions? So far, so good. All right. And you can do this signal by signal, essentially level by level. Or you can do this at the first input change. You can draw these 3 changes at the same time and these 3 changes at the same time. So it's up to you. I like to do it, signal by signal. All right. So let's have a look at a different function, and just to show you another example. So in this case, my initial input is 1, 1, 1, 1, 1, 1, which will make this a 0, this a 1, output is a 1. That is my initial condition. And let's say at time 20, I change my input to 1, 0, 1. So B goes from 1 to 0. At that point, the top signal will evaluate to 1. The bottom one becomes a 0. The output remains a 1. So both of these are input conditions producing a 1 at the output. Right. So, and then let's put that in the timing diagram. So A is always 1. C is always 1. B is 1 until time 20, and then becomes a 0. Those are my input curves. All right. So let's say E depends on B and C after 10 nanoseconds of delay. And my initial value for E is 1. Oops. My initial value for E is a 1. My initial value for D is a 0. And the initial value for F is a 1. These are based on my original condition of ABC equals 1, 1, 1. Right. So let's say when B goes from 1 to 0, that's the only change at the input. So we can do the analysis based on that singular change. When that goes from 1 to 0, after 10 nanoseconds, E will also go from 1 to 0. Right? E depends on BC after 10 nanoseconds. So 10 nanoseconds after the B change, E will go from 1 to 0. So we're going to continue E until times 30, and then let it go back to 0. Right. What about signal D? Well, for this B change to propagate to D, we need to go through 2 gate delays, this inverter and the gate, so 20 nanoseconds in total. Right? So 20 nanoseconds after the B change, D will go, so at time 40, D will go from 0 to 1. And now we're going to look at F, the final output. So F depends on both D and E. So when E first changes, after 10 nanoseconds, F will also change. So at time 40, f will go from 40, from 1 to 0. But you see, at time 40, d goes from 0 to 1. So after another 10 nanoseconds, f will come back to 1. All right, please forgive my inaccurate drawing. So this is like time 30. This is time 50. All right. So again, we do this gate by gate evaluation. And then whenever there's an input gate input change, I will examine whether that impact has any output, whether that change has any impact on the output of the gate. And if there's an impact, I'll update the gate after the gate delay. And f gets updated twice, because it gets updated once when E changes, and gets updated again when D changes. Right. So here we're observing an interesting behavior. Both of these input patterns, 111, 101, they should produce a 1 output. But if you actually analyze the timing behavior and considering the delay of that inverter, the output temporarily glitches to 0. Right? That's kind of annoying. You expect the output to stay at 1, but in reality, it might change to 0 and then back to 1 after a little while. And this behavior is called a static hazard. So I think here they have a better drawing of the same diagram, essentially the same as what I did earlier. So in this case, the output momentarily goes to 0, and this is called a static hazard, and like unreliable output while the input is still changing. And you can show that behavior in a timing diagram, or you can also put that in a timing table, essentially the same as the diagram, but instead of drawing all the lines, you just write down the signal value at a particular moment. So time 40, f goes to 0. Time 50, f goes back to 1. Right? These are equivalent timing representations. And static hazards are unwanted switching transients at the output upon input changes. So essentially, more specifically, that is upon a 1-bit input change. You change 1 bit of the inputs, you expect the output to remain the same, but the output momentarily goes to the wrong value. That is called a static hazard. There are 2 kinds of static hazards. Static 1 hazard means I want the output to be a 1, but it momentarily goes to 0. Static 0 hazard is the opposite. And what we're observing here is a static 1 hazard. The output should be 1 for both of those 2 input patterns, but it momentarily goes to 0. So this is a static 1 hazard for that 2-level sum of product circuits we examined earlier. And take a guess among these 4 people that we have encountered in the class, who identified static hazards to be an issue? It's one of them. Just give me a random guess. It's not Quine, because Quine didn't do much work in circuit design. Yeah, the other 3 people, they spend their whole life designing, optimizing, and analyzing circuits. Just write me a random guess. Yes? Hamming? Why do you think it's Hamming? Error detecting and error correcting codes. Yeah, I think that's a reasonable guess. But his work is more about those binary numbers. And binary and Boolean are some similar and related, but different concepts. Right? So he studied a lot about number series, not so much about the operation of digital circuits. Yeah.
Because that relates to electrical.
Yes, yeah, it relates. It is McCluskey. He really pioneered many things. For one thing, this notch minimization algorithm for combinational circuit, but he eventually did more studies in sequential designs. So this is, like a timing-related behavior, which is sort of related to sequential circuits. And later, we'll see how to model actual sequential circuits using a finite state diagram, which is also one of the topics pioneered by McCluskey. So it's actually McCluskey. He found static hazard, and he also had a lot of contributions in reliability and security of digital circuits. Right. So what we saw earlier is that when the signal goes from 111 to 101, we have a static hazard. Let's also examine the same behavior in the opposite direction. So suppose, I'm just going to draw it really quickly. A is 1, B is 0, and C is 1. But instead of changing B from 1 to 0, I change B from 0 to 1. Again, both of these conditions should give you an output of 1. Right. So let's say B changes from 0 to 1 at time 20. And then it remains at 1. So what's going to happen to signal E is that after 10 nanoseconds, E originally, okay, let me put down the original value, 101. D is a 1, E is a 0, F is a 1. So E starts with a 0 after 20 nanoseconds, so times 30. E goes from 0 to 1. Right. What about signal D? Well, signal D will change 20 nanoseconds after B change because there are 2 gate delays between B and D. So D starts with a 1, and at time 40, so 20 nanoseconds after the B change, it goes down to a 0. Right, now let's have a look at the output. The output in the original condition is a 1. And when E changes from 0 to 1, if you look at the bottom, so let E goes from 0 to 1, the output remains at 1. Right? Because the top input is a 1, the output is 1, essentially independent of the bottom input to the final gate. So E, F will remain 1. Well, even after D with a longer latency changes back to 0, at that point, E input is already a 1. So the output of this gate remains a 1. So in this case, we really have no hazard. The very same 2 input patterns. You go from 111 to 101, you have a static hazard. 101 to 111, you do not have a static hazard. And this tells us that hazard is a directional behavior. It happens only under some limited directions when that hazard variable changes. Right. Does anyone know why we do not have a hazard in this case? Right, based on the circuit diagram. Any intuitive explanations? Right, why my output remains a 1 when B goes from 0 to 1? It does, right? The invert is what creates the imbalance between the top and bottom paths. The top path is longer. And when your B changes from 0 to 1, the bottom path will become 1 first before. So this one happens early. This one happens late. When your 0 to 1 occurs first, the output will be forced to be a 1 because one of the input to the OR gate is a 1. At that point, essentially the bottom guy takes control of the output behavior. So even if the top one changes a bit later, it does not affect the output. Right, you can analyze static hazard using circuits by just tracing through different signals, finding the imbalanced paths. But you can also do that analysis using K-map, which is a lot more convenient, isn't it? So K-map, these 2 AND gates translate into 2 impedance, what I put in that K-map. And static 1 hazard for a sum of products, a 2-level SOP expression happens when you have these 2 adjacent ones, like here and here, that are not covered by a shared impedance. Or you can say you have 2 adjacent impedances that do not overlap. In that situation, we would have a static hazard. Because to make the output a 1, different sides of the OR gate need to make the contribution. When you change 1 bit, let's say from 111 to 101, these 2 signals flipped. And that only happens when your hazard variable between those 2 adjacent ones changes from 1 to 0. So I'd like to draw an arrow pointing from the 1 side to the 0 side. That's the only disagreeing input bit between those 2 midterms. And that bit has to go from 1 to 0 to trigger the static hazard. Essentially, if we do the same analysis of which one reacts quicker and which one reacts slower, we'll let it change from 1 to 0. The bottom one will go to 0 first, before the top one go to 1 a bit later. And that is probably already too late to prevent static hazard. Static hazard would have already happened when the bottom one changes to 0 first through the shorter path. All right. And given this root cause, you can prevent it by adding in one additional implicant to your SOP expression, essentially giving up minimality. Use this non-minimal expression or non-minimal implementation with 3 implicants, but preventing any 2 adjacent minterms from not being covered by a shared implicant. Right? Essentially cover all the adjacent minterms with some implicants. That will eliminate static hazards. Why is that? Well, again, if we look at the very same pattern, 1, 1, 1 goes to 1, 0, 1 on ABC. The bottom one will remain 1 throughout your computation. And that will be the one contributing the one output, independent of what happened, or the glitches happened on the other side. Right? By introducing this one additional implicant, you essentially make sure that when you make the 1-bit flip on the inputs, there's always a gate that consistently produces the output of 1. And that 1 sets the OR output to a 1. Okay, the very same analysis, you can do it in the circuit together with timing diagram, or you can do it in a K-map. Right? But I would recommend you to still have this picture of circuit in your mind so that you know precisely what is happening in terms of timing behavior, in addition to, if you want, memorizing the rule through K-map. Any questions? All right, so if we have something for an SOP, I guess you would imagine we have a similar thing for a POS. And indeed, for SOP, we have static 1 hazard when the output goes from 1 to a momentary 0 back to 1. For POS, we have the opposite behavior. So the output should be 0, but it momentarily goes to a 1, and this is called a static 0 hazard. And this only happens in a POS. And the reason is kind of similar. You have this imbalanced path in your implementation. And if you look at the K-map, there are some adjacent zeros that are not covered by a shared implicants. So between the 0 over here and 0 over here, you would have static hazard. But take a guess on which direction the hazard happens. Is it from 1 to 0 or 0 to 1? Right, by this principle of duality, let's say, if I use that as a general term, SOP and POS are opposite to each other. So for SOP, hazard happens when you change a variable from 1 to 0. For POS, it happens when you change a variable from, SOP is 1 to 0. POS is 0 to 1. It happens when your input starts with A, B, C, D equals 0, 1, 0, 1. And when you change it to 1, 1, 0, 1, you would have a static 0 hazard. So let's say if I put down those values, A, B, 0, 1, C, D, 0, 1, and then I'll change my A variable from 0 to 1. Again, we have these 2 imbalanced paths. The one through the top and the one through the bottom with an actual inverter. And because it's actually inverted, when I change this to a 1, this one will become 1 first to set the output to a 1 before this one comes down to 0. So the top pass will go from 0 to 1 first before the bottom pass takes a longer period of time to give you a 0. So momentarily, while the first one is a 1, the middle one is still a 1, output momentarily becomes a 1. All right, and later on, you can do a more detailed analysis using timing diagram if you like. And in fact, in this picture, we have multiple static 0 hazard. Again, it's a way to, it's a process of finding adjacent max terms that are not covered. So between this 0 and this 0, you would also have a static hazard. Between these two adjacent zeros, you have a static hazard. Between the top and bottom, you would have a static hazard. Right? Those are illustrated by the dotted lines in the diagram. We essentially do the same for SOP. We find adjacent minterms not covered by a shared implicant. Yeah, any questions? Yeah, that's everything we're going to talk about timing. So that concludes my discussion about timing. So we talked about propagation delay, contamination delay, and this specific behavior with combinational circuits when you have this imbalanced paths and you have adjacent minterms or not max terms not covered by a shared implicant or implicates. And you can fix it by including additional implicants or implicates in your function. All right. So with that said, let's refresh our mind a little bit and we'll move on to a different topic. And this is the last part before we start talking about sequential circuits. And these are called Datapath components. We have been building circuits using gates. We translate Boolean expression into a circuit by putting down AND and OR gates. You can also build circuits using some different components. One of them is called the transmission gate. This is a way to connect or disconnect 2 points using an enable or control signal. And this is built with 2 transistors, one NMOS, one PMOS. The reason why we put on that pair is because they do a different kind of transmission better. PMOS is really good at transmitting 1, and MOS is really good at transmitting 0. And we're sending complemented enable to those 2 MOS devices. You can transmit both 1 between A and B and also 0 between A and B very efficiently. Efficient, I mean without much signal degradation. You can bring this, again, purple slides. Don't have to worry about it if you don't want to deal with CMOS and CMOS technology. So you can put down 2 additional inverters before that transmission gate to build a tri-state buffer. So these 2 inverters, logically, they don't do anything. You invert the signal twice by involution, you get back to the original signal. But that will improve the strength of the signal. So let's say your 1 is slightly degraded to be a 0.9, 0.8. Then with the 2 inverters, you can get back to the original driving strength. And again, we're using the enable to control the connection between A and Y. So if enable is 1, if you look at the truth table, if enable is 1, output is the same as your A input. If enable is 0, output is Z, which means high impedance, essentially disconnected. And we use these tri-state buffers to design a bus. You might have heard about the word bus in a computer system. A bus is a way to create connections between a number of inputs and a number of output devices. So for example, you might have a processor that is connected to 3 input devices, camera, mouse, and keyboard. And you could build a point-to-point connection. Or you can also build this kind of a centralized bus that connects all 3 input devices to the output, right, to the receiver. And in that scenario, if you send them on the same metal wire, you don't want multiple devices to send in signals at the same time. That will create a contention scenario, and the signal will be either lost or corrupted. So what you do is you put down 3 of these tri-state buffers as a selection mechanism. At any point, you only turn on one of the enable so that one device is sending in like a stream of binary data to the receiving device. But that prevents multiple devices from sending in or putting down values on the bus at the same time. You can also use it to control a 4-bit adder using a bunch of these selectors to select one of the inputs to be added with another 4-bit input, let's say. All right. So this tri-state buffer can be used to build a component called multiplexer. Multiplexer is a way to select multiple inputs to connect to an output. So we use a select input to control which of these inputs can flow to the output. So let's say if select is 0, essentially the top tri-state buffer will be connected. So I0 will flow to the output. So they're connected. If select is a 1, the bottom tri-state buffer will be activated. So output is the same as the bottom input. And this is essentially like a 3 input, 1 output function. And you can illustrate its behavior in a truth table. So when your selection input is a 0, output is the same as I0. They are connected. If your selection input is a 1, output is the same as the I1, the other inputs, because they're connected. Right. Between 2 sources and 1 destination, you can select the connection by controlling the select inputs. All right. So this circuit, essentially, this is a 3 input, 1 output circuit. So you could build it with tri-state buffer. That's one choice. You can also build this using some kind of a 2-level SOP expression. So I'll just do that real quickly. So to do that implementation, you drew a K-map, right? And then just for convenience, I put S on one side, I1, I0 on the other side. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. When select is 0, I0 will go to the output. So I have 0, 1, 1, 0. Let me use a better color. When selection is 1, I1 will go to the output. So 0, 0, 1, 1. And if you want to implement that using a 2-level SOP, we find the impedance, and then we can express the output Y to be as prime I0 plus S I1. Right? And then you can make this into a 2-level sum of product circuit. This expression kind of makes sense. If S equals 0, then this one becomes a 0, this one becomes an I0, so Y equals I0. If S equals 1, this is 0. 1 dot I1 gives you I1, so Y equals I1. Right, a way to connect Y to different sources by asserting the selection signal. Yeah, any questions? So what I've just illustrated is a 2-to-1 mux, selecting between 2 input sources to 1 output destination. You can also build a 4-to-1 mux or 8-to-1 mux by using more control inputs to select 4 inputs to 1 output connection, or 8 inputs to 1 output connection. Right, essentially, for example, for this 8-to-1 mux, if my input is 0, 0, 0, I0 will connect to the output, and the other inputs will be just disconnected. If they are equal to 0, 1, 0, I2 will connect to the output by the same idea as a 2-to-1 mux. You can build this as a 6-input function and do logic minimization if you like. Or you could build that using some smaller multiplexers. You can use smaller switching devices to build larger switching devices. So let's say I have 3 2-to-1 muxes, and my goal is to build this 4-to-1 mux using 3 2-to-1 mux. Now I'm indeed able to support 4 data inputs. I can put my I0, I1, I2, I3 over here. Right? And the goal is to implement this Z output that does a 4-bit selection. What do? Well, I can connect them together so that everything goes into a single output. And now I need to put down the appropriate selection signal. I want AB equals 1, 1, for example, to select I3. That is my goal. I want input of 1, 0 to select I2. So what do? Well, I want to activate essentially this pass if my AB input is 1 and 0. And by the look of it, this signal is connected to the 1 side of the 2-to-1 mux. This signal is connected to the 0 side of the 2-to-1 mux. So I can put down the B variable over here, A variable over here, to make the selection. All right, just to complete the picture, I'll put the B variable for the top 2-to-1 mux as well. And we can verify its behavior. AB equals 1, 1. 1 selects the bottom pass, 1 selects the bottom pass, so I3 goes to the output. AB equals 1, 0, 1, 0, that's I2. 0, 1, so 0 is on the top, 1 is at the bottom, so I1, and 0, 0, all the way going to the top, I0 goes to the output. Right, sort of like put A on the right positions because it's like the more significant bit, so it has to make the master decision, and B is like the secondary, the least significant bit. So put that on the first level to make the more fine-grained selection between adjacent midterms. By the same analysis, you can put 2 4-to-1 mux together with 1 2-to-1 mux to build an 8-to-1 mux. Right, by the same idea of putting them in this kind of a triangular shape to support a higher width selection. Right, so that's about the construction of the multiplexer. You can do tri-state buffer. For a small one, you can do it by 2-level SOP or 2-level POS. And for the larger one, you can do a modular decomposition to use small mux to build larger muxes. And I told you that we can use these components to build circuits. And let's see how we can use them to build some different, more complicated functionalities. Starting with some analysis examples. I give you some muxes, and then I connect them to some A, B, and constant inputs. Could you try to figure out the functionality of the first gate? I'll give you half a minute to work on that exercise. Try to recover the output behavior as a Boolean expression in terms of A and B. If you have more time, feel free to also work through the other examples. All right, I'm afraid time is up. And then I'll do this on the board together with you. So you can think about its behavior in terms of a 2x2 K-map or 2D truth table. When A equals 0, output will be 0. When A equals 1, you look at this column, output is B. So B is 0, output is 0, B is 1, output is a 1. And that's really, this is an AND function. So you get A dot B at the output of the mux circuit. Right. Similarly, we can look at it column by column by different values of the selection inputs and see what you get. So in the second example, A equals 0, output is B. A equals 1, output is 1. So this is an OR gate. You get A plus B. Third example, A equals 0, output is 0, 1, the B variable. A equals 1, the output is the complement of B. So I flip the B variable to 1, 0, and that gives you an XOR function. So A XOR B. And finally, in the last example, A equals 0, output is 1. A equals 1, output is B prime, so 1, 0. And this is the complement of the first table. So this is a NAND gate. So A dot B complement. And you see, essentially, multiplexer is a universal set because we can build the NAND gate. Right? Actually, you can also build the inverter, any other gates, of course. But NAND gate by itself is a universal set. So multiplexer is also a universal set, which means you can build any functionality using a multiplexer. Right. So I have a more complicated examples. Again, to interpret the functionality of such a max circuit, we go through level by level, from inputs to outputs, and then gradually construct our Boolean expression. So at the first level, I have, well, if A is 0, so I can write it as A prime dot 1 plus if A is 1, the output is C. This is the Boolean expression way of recovering the output function. You can do that through K-map, as I showed you earlier, or you can do that by just multiplying these two inputs with complemented A or non-complemented A, the selection variable, and then you can write it out as the output Boolean expression. This one essentially is the same as A prime plus AC, which is A prime plus C, a Boolean expression in the middle. And at the last level, again, you can use a 3-variable K-map. And I would recommend you to also try it out. But I like to use this multiplication method by multiplying the first input on the 0 side with B prime, and the second input on the 1 side with B. And that would be my output Boolean expression. So A prime B prime plus A B prime C plus BC prime. All right. Essentially, the idea is to use the selection variable and then complement the inputs on 0 and 1 side with non-complemented and complemented selection variable respectively. This is a Boolean way or algebraic way to construct the output function of a mux. All right, yeah. Any questions about this? All right, so these are some analysis examples. A small analysis example using K-map and a larger analysis example using Boolean algebra. But you can always use whichever method that you find more convenient. And I would say K-map is usually more convenient. All right. So now we're going to move on to the next question. Again, we have usually 3 learning objectives: analysis, implementation, and optimization. We're just seeing analysis. Now we're moving on to implementation. Given some general function, right, the question is, how do I implement that using some multiplexers? Well, I need to connect some of these input variables to the left and some of the variables to the bottom as selection signals. So let's say if I put AB at the bottom, let's see what we get. I'm essentially decomposing the function into different, different sections. A section corresponds to AB equals 0, 0, right? Another section or quadrant corresponding to AB equals 0, 1. So really, by putting AB as a selection signal, you're cutting this K-map into 4 different columns corresponding to the 4 AB conditions. And within each column or within each section, we're trying to find a Boolean way or algebraic way to express the function. In this case, if you look at those 2 signal values, 0 and 1, how would you describe that in terms of the missing variable C? It is just C. C equals 0, output is 0. C equals 1, output is 1. That tiny Boolean expression is F equals C. Look at the second column. You have 1, 0, and that is a C prime. The next column, 1, 1. The output is a constant 1, so we can put a constant 1 at the bottom. And finally, this 0, 0 corresponds to a constant 0 in the 1, 0 case on AB. So mux implementation is really a way to cut the K-map into different sections. And now instead of implementing the full 3-variable function, you're just implementing it using only the missing variable. All right. And let's also try something different. Let's say if I use A and C to cut my K-map, which is perfectly doable. You don't have to restrict yourself to any 2 particular variables. You can use any variables as the selection signal and the other variable as some of these input signals. So if you cut it by A and C, So I'm essentially creating this kind of a cut. Right? This is A equals 0, C equals 0. A equals 1, C equals 0. A equals 0, C equals 1. A equals 1, C equals 1. These are the 4 quadrants. And the goal is to represent the remaining function using the missing variable b. And let's say you have this one, the first one, 0, 1, that is exactly the same as b. So I put down a b over there. The next part, 1, 0. Output is also just b. Right? If you have a careful look at the b variable, it is the same as the output. So the 1, 0 case also gives you the b variable. And what about the next? Well, I can do 0, 1. Output is the complement of b. So I put down the complement of b. And finally, the last bit, 1, 0, that is just b. All right. So K-map or max implementation corresponds to a way of cutting the K-map, essentially assigning a partial condition on some variables and then represent the kind of remaining function using the missing variables. You could even use a smaller max to implement the function. So let's say I put A as my selection signal. Well, actually, for convenience, I will use C, so that I can easily see whatever row corresponds to. So if you use C as a selection signal, when C equals 0, output is these two minterms, and that is B equals 1. So we can put down B on top. And when C equals 1, output is 1 when AB equals 0, 0, or 1, 1. And that is the XNOR function between A and B. So you have to put down a function of A XNOR B at the 1 input. If this is the only max you have, you probably need to use some gates to implement this NOR function. Or if you have another max, you can implement the XNOR function using another multiplexer. Any questions? Yeah, I know this part is we're coming back to K-map and do a lot of manipulations. So this one probably requires some exercise to get you really comfortable with it. All right. So this idea of max implementation really boils down to this concept of Shannon decomposition. So Shannon decomposition is a theory saying that any function, you can decompose it into 2 phases. Right? By assigning a variable to 0, you do one implementation. By assigning the variable to 1, you do a different implementation. Like each of these implementations is a smaller implementation compared to the original function. Or in terms of K-map, we can cut it in half, using any line you like. Let's say here we're cutting the middle by the A variable. And then we just need to implement 2 smaller implementations and then construct them through a mux to build your overall circuit. The original expression implementation involves 4 prime implicants based on this 4-variable K-map. And if you cut it into 2 separate functions, this function has 3, this function has 2, like the implementation complexity for each individual module is reduced, even though overall you may not get the most optimal implementation, because you lose any opportunity to share like implicants between the 2 sides. All right. So Shannon decomposition is developed by, of course, a guy named Shannon, who is also the recipient of the first Shannon Award. He's the father of information theory, cryptography, and artificial intelligence. So he really analyzed many different topics. I think he developed some encryption decryption algorithms, and he also developed like some theory for chess computers. That's the reason, and also like natural language processing, and that's the reason why he's the father of artificial intelligence. He's the first guy to use Boolean algebra to build circuits in 1937 to 1938. You see, that is about like 14 years before we have K-map and the logic minimization algorithm. So this is really some very early work on Boolean circuits. He was using Boolean algebra to build a telephone routing switches, which kind of makes sense. At that point, telephone company is the driving force for innovation in digital design. We have this Bell Lab. Right now, this is called AT&T Bell Lab. So they have an origin in the telephone industry. And he later proved that application of Boolean algebra can construct any logical numerical relationship. Essentially, you can build any circuit using Boolean algebra. Right? Not just circuit, any functionality, any application you like using Boolean algebra. And he, again, as surprisingly, has also worked at Bell Labs together with those other guys. And he started a bit earlier, doing some wartime research on cryptography, and later more about crypto, AI, language processing, and also Boolean circuits. All right. So again, in that lab, there's some amazing people, and they must have talked with each other and then generating new ideas. And this is Shannon's work on his decomposition theory from that paper in 1938. But it's surprisingly readable. You have Boolean expression involving a bunch of variables. You can set that variable to 1, like a constant 1, to simplify the implementation, and then multiply that result with the corresponding variable, set it to 0, right? Multiply it with the complement of the variable. And that's essentially how we represent the output behavior of a mux, a way to decompose function into individually smaller subfunctions. So I also uploaded this document to Canvas. If you want, you can have a just look it for fun. And you see, you can apply decomposition on one variable. You can apply it on two variables, like in that 4-to-1 mux. We use 2 selection signal. And you can also do that on essentially all the variables. At that point, you get a min-term expansion. And because we know min-term expansion can represent any Boolean function, we get to prove that we can use mux to build any function. Right. So what do I mean by the relationship between mux and min-term expansion? So let's say I have a 3-variable function. If I have the luxury of using 3 selection signals, I can just connect all the 3 selection inputs, A, B, C, to the bottom of the mux. I use them to select some constants. So if ABC is 0, output, I want my output function to be a 0. So I just connect the constant 0 to 0, 0, 0. 0, 0, 1 is a 1. 0, 1, 0 is a 1. And then a 0. 0, 0, 1, 1. That's essentially the output column of my truth table based on ABC. Right. After enough decomposition, the function does not depend on any of these variables anymore because they have already been decomposed. So you're just going to put down a bunch of constant zeros and ones to construct the function. A way to implement a min-term expansion directly without any Boolean algebra. All right, so that's the relationship between mux and min-term expansion. Mux and minimization are also related. What I mean by that is this function, you can implement that using SOP. You can also implement that using mux. But finding the best implementation is not straightforward because you can do cutting so many different ways. You can use AB to do cutting. You can use BC, BD, AD, right? Any of these pairwise combinations. And to find the best implementation, you really need to try many things. So that's the reason why multiplexer is not usually used as a minimization component. You can use it for implementation, actually for convenient implementation, but oftentimes you don't get minimality. And given this circuit, I really don't know how to cut it, how to find the best cutting. I'll probably try this first. And then this one gives me like 1 gate, 1 gate, 1 gate for a single 1 or 3 ones. I need to represent that subcube, 2 by 2 K-map as a Boolean expression. So I need some additional gates. If I do cutting in a different way, let's say cut here, cut here, cut here. Again, I need 3 gates whenever I have an odd number of ones in that subfunction. Right? Try putting that function in a 2 by 2 K-map, and you will see you have 3 ones, and 3 ones requires an OR gate or NAND gate, AND gate, etc. Right? So it's really not an easy task to do minimization with multiplexer. Does anyone visually see a better implementation? I do see a better implementation. You can cut it like this and like this based on the a variable. So a equals 0, a equals 1. You can put a as one of your selection. And then this is d equals 1, d equals 0, d as another selection. And now again, you have 4 quadrants. You can implement each component as a smaller expression. So a0, d0, that is the function of c. This is sub-expression of c. So a equals 0, d equals 1, that's an expression of b. Right. I think I should do some color coding. And that is b. The first one corresponds to c. And then the next expression would be top and bottom. And that is b equals 1. So b in the a1, b0 case, b. And finally, that singular 1 has to be implemented as the product between b equals 1, c equals 0. So that one requires one additional gate. B equals 1, c equals 0. And that is one additional gate. Decomposition is a way to cut the K-map, and finding the best one is not easy. I have to try many things before finding this solution. So I'd like you to also think about the correlation between Shannon decomposition and map-entered variable. So in map-entered variable, let's say you have a K-map with both A and A prime, right? You would have 3 K-maps. With Shannon decomposition, you decompose it based on that variable. So A equals 0, you have 1 K-map. A equals 1, you have another K-map. And then you can find the minimum expression from each K-map and then compose them using a mux, or by taking the sum of these 2 terms. And that is a valid implementation of the function. You cut it by A. So A prime, A for 2 different K-maps. And each of these functions will be represented by the remaining variable, B and C's. Right? That's different from what we did with map-entered variable. So for the very same K-map, with MEV method, we have 3 K-maps. We have this additional A independent case. Right? And this K-maps also look somewhat different from what I had in that Shannon decomposition method. So if you put them side by side, and you compare this expression versus the expression on the right by adding together these 3 implicants, you will see that, well, this one has 2 variable implicant, 2 variable implicant, 3 variable implicant. Over here, you have like a 2 variable implicant, 3 variable implicant when you apply distributivity, and another 3 variable implicant. And if you treat that as a logic minimization result, this one is not optimal. That one is optimal. Right? This shows you the limitation of Shannon decomposition. When you decompose, the sharing between the A and A prime side is limited, and you tend to miss some of these things that can be shared independent of the A variable. So again, MEV is a method that can often guarantee minimality. Shannon decomposition is a very nice theory that allows you to construct any function. But if you use it for minimization purpose, we usually do not get optimality. All right. Yeah. Any questions? All right. So with that, I'm going to quickly go through 2 other components. One of them is called a decoder. Decoder is a way to represent 3 inputs in a more expanded format. So let's say you have a 3-input binary number, 0, 1, 0. Decoder will convert that into a single 1 at the output among all the 8 combinations. So if you have an input of 0, 1, 0, which in binary means number 2, then y2 will be a 1. All the other outputs will be a 0. Right, so a way to expand your binary number into a bunch of zeros and ones with 1 at the position whose index corresponds to your input number. Right? And again, this is just a function. And if you really want, you can implement that using some combinational logic, using AND gates, some inverters. So 1, 1, 1 will make the last output a 1, and this one is actually a larger 4-bit decoder implementation. And you can use decoder to build function. Decoder essentially gives you a bunch of minterms. Because, let's say y2 is 1 only if input represents 0, 1, 0. So in terms of a Boolean expression, each output is a minterm. And the question of implementing a circuit becomes a question of collecting the minterms using an OR gate. So let's say this function, the first function, has minterm number 1, 2, 6, and 7. And if I want to implement that, I'll just connect minterm number 1, number 2, number 6, number 7 into an OR gate, and that implements F1. For the bottom one, you have 6 minterms, so you can collect all 6 minterms using a single OR gate. Or you see there's only a single max terms. So you can get that max term by, this is index number 5. Index number 5, because ABC equals 1, 0, 1. So what you can do is you can take this minterm, and if you complement this, that becomes the max term. A plus B plus C prime. And that is really what you need for F2, a single max term, by inverting the corresponding minterm. Then you have a choice for F2. You can collect 7 minterms or inverting the singular max term. And you can also build larger decoder from smaller decoders. What that means is, let's say we have a 3 to 8 decoder generating all the 3-bit minterms. You can build a larger decoder with like 4-bit minterms. Let's say I want A prime, B prime, C prime, D prime to come out of my first output bit. What you can do is you can create an enable signal to this decoder. And enable, essentially, if enable is 1, it will work like a regular decoder. If enable is 0, it will just set all the outputs to 0, right? To disable that component entirely, flush out the output with zeros. And that, if that is connected to the complement of A, so the top side will only be working when A equals 0. So these minterms depend on A equals 0. So essentially, you can represent it as an A prime in the output minterm representation. And any minterm you have on the right have their enable signal connected to A, so they can be represented with A multiplied by the corresponding BCD minterm. And that is exactly minterm number 8. 2 smaller decoders with the additional enable signal connected to complemented and non-complemented variable allows you to construct 4 variable minterms. And if you want to implement this 4 variable function, put on an OR gate, connect them to several of the minterms, you get the expression. All right. Just going to show you one realistic example before we conclude the lecture. So decoder and multiplexers are used very commonly in memory construction. So memory has a bunch of these blue cells. Each of them is, you can think of it as like 1 bit of the data. And you have multiple lines. Like every line, think of it as 1 word, a multi-bit group of data. And to really write something to the memory, you want to essentially enable one of these lines. Or also read something from the memory, you want to enable one of them. To get singular enable signal, you can use a decoder, which takes your 3-bit address, convert that into an 8 different signals, each representing 1 minterm. So whenever you put down an address, one of these enable signal will be 1 to activate 1 row, which is 1 word in your memory. And you can then put the data through the top, load them into the cell, or read the data from the bottom. So this benefit of having a single 1 within that 8 bits is really a convenient way to make a selection within 8 different components. But you see our memory nowadays is a lot larger, right? They have like 32 64-bit address. So we typically have multiple levels of decoders to handle this decoding process. Like having a single decoder for 64-bit data is just too much. You cannot accommodate 2 to the 64 different output ports. All right. So I'm going to save the encoder discussion for the next lecture. So here's a conclusion of what we talked about today. We talked about timing of combinational circuits, starting from individual gate delay to finding the longest and shortest path in a circuit. Represent timing behavior in a diagram, also finding static hazards using from the circuit and timing diagram, or you can also do that through the K-map. We talk about mux and decoder, different components where you can also build circuits by decomposing the function or collecting minterms with decoders. And tomorrow we're going to continue with encoder to just finish up this discussion, and we're going to move on to some sequential elements. Some circuit components have memory capabilities, like being able to memorize values. All right. Yeah. If anyone has questions, just we can also talk about them. That was a lot, yes. You see, whenever we start to wrap up on a topic, we just have a lot of these miscellaneous, tiny little things here and there. Yeah, the other thing is, we have a holiday, Monday of next week, so I sort of have to. No. Yeah, Labor Day. Look completely surprising. Yeah, and for that reason, I also have to, accelerate it a little bit and then skip some topics. So you might have noticed a mismatch between what I tell you to prepare from last Thursday's workbook versus today's lecture. Yeah. But you see the slides are available earlier, so you can also check out the slides as a study guide. Last lecture. Yeah. No. Yeah, just presentation.
Is last lecture review?
If time allows, right, depending on how many presentations we have. Yeah. That's right. So, okay, Wednesday's workbook will be due on Friday, essentially before the exam, right?
Is that like new concepts or all the concepts?
It's going to be semi-new. Tuesday is probably going to be new. Wednesday is like how many things have we learned come together. Let's say these multiplexers together with sequential circuit, together with adder, we use them together to build complicated functionalities. Right? Not really building complex functionality, but finding a model to describe that behavior and be able to build complicated and scalable computation.
Does that mean there's a weekend workbook on
No. So everything will be done by the final exam.
Is there really a good reason?
So when you build a circuit with multiplexer, you are essentially doing Shannon decomposition. So when I say cutting the K-map, so Shannon decomposition tells you that once you divide it by a variable, let's say x1, the rest of the function does not depend on x1. x1 is set to a constant. To simplify the function, and then you implement it with the remaining variables. That's essentially what we did like over here, right? When we break it by the C, then the other two implementation does not depend on C anymore. Right? So formally speaking, that's Shannon decomposition, but casually, it's just cutting the K-map. For the fall?
Yeah.
Yeah, very nice.